heard a lot today about the necessity of doing precision cosmology, perhaps at the level of 1 part in 10 to the 4 and 1 part in 10 to the 40th if you're on the depressive side, pessimistic side. But the hallmark of Al's career, I think, is accurate cosmology. He's worked on a tremendous number of experiments whose foci have really revolved around the impact of minimizing the impact, rather, of systematic effects. Whether it was his work as a grad student with Smoot or later on with Kobe, and then his really novel instruments that he's been working on for the last several years, including Pixie, Piper, and other, as well as the work that his team at NASA Goddard Space Flight Center work on, is really characterized by this pursuit of accuracy. And I'm very interested to hear what we will hear from Al with regard to future experiments to measure these interesting theoretical implications.
Well, thank you. It's a real pleasure to be here. We've heard this morning about we have a standard model for cosmology, and it's not just the microwave background that exists. Our standard model of lambda CDM, where the universe is dominated by a cosmological constant and cold dark matter with a small admixture of baryonic matter. This passes an enormous range of tests over an enormous range of time scales and physical scales. I'm supposed to drop this at the end of the talk, I think. And so, we have these disparate tests that all agree with a standard model here with only 6 adjustable parameters. And if we add inflation, maybe there'll be a 7th parameter if we ever see B modes. And that's good. It's good to have a theory out there, or maybe even call it a paradigm to guide a test of this. But we've been warned against hubris, and there are examples of other successful cosmological models. Here's the Ptolemaic model, in which the Earth is the center of the universe, and we are taught carefully in high school usually to poo-poo this. Those stupid Greeks, what did they know? But this was a cosmological model that did what it was supposed to do. It predicted the positions of the planets on the sky with only 14 adjustable free parameters. Later, eventually, the number of epicycles grew to 28. But this worked. This did what it was supposed to do, and it lasted 1,500 years until observations finally overthrew it in favor of a much simpler model. So with our lambda CDM model now, that's been going with 6 parameters for of order 20 years. We've got a ways to go until we get to 1,500 years. So we ought to maybe not take ourselves entirely seriously that lambda CDM is the ultimate theory here. One of the tests of this that I'll be focusing on, and is a focus of this workshop, is looking for evidence of an inflationary epoch through its signature in the microwave background polarization. And the basic idea here is that if you have an inflating space-time that creates a gravitational wave background, those gravitational waves propagate through the universe, and at much later times they interact with the photons of the microwave background to impart a small amount of linear polarization, shown here. The polarization of an arbitrary field can be decomposed into pieces that have even parity and look the same in a mirror reflection, and odd parity that have a handedness. And the gravitational waves make both of them, but other things in the universe can make the even parity ones. So the name of the game for observers is to go measure the linear polarization and see if we can find, on angular scales of a degree or larger, evidence of polarization with a handedness. That's thought to be a smoking gun signature of inflation. And if we see that, we would conclude that something like inflation occurred in the early universe. And that means that we've then measured the energy scale of inflation is tied to the amplitude of these B modes. And since these are caused by gravitational waves during a quantum period of the universe, that would show us observational evidence that gravity obeys quantum mechanics, which would in and of itself be an astounding discovery. So if we want to measure this, of course, we're going to have to do that with some sort of an instrument. Perhaps it's something very simple here where you put up, but my talk here today is going to be outlining some of the design challenges that hit us when we're trying to measure these incredibly tiny signals. We heard earlier that the signals we're looking for here are small. They're of order nanokelvins. I plotted here the power spectrum of the B modes. So it's the amplitude of the signal as a function of angular scale, for inflation at a minimal inflationary of R of 0.01, which is 7 times below our current upper limits. You're seeing here, you're talking powers here of a few nanokelvins on large angular scales and dropping off rapidly to smaller scales. A bunch of upper limits here. Measurements are now starting to actually see B modes, but these are not the primordial B modes. This is the E mode signature that's been warped by gravitational lensing by the effects of matter between the surface of last scattering and us today. So these are interesting as a test of gravitational lensing, but they're not the primordial signal, which could be here, or if you're in a depressive mode, it's 10 to the 40th times smaller. But it's very hard to go to a funding agency and tell them you want to do 40 orders of magnitude. So we'll stick with the idea here of looking for signatures at the level of R of 0.01 to 10 to the minus 3, which is thought to be the dividing line between large field and small field inflation. Now the problem here is that a few nanokelvins is small, so you need a very sensitive instrument. You have to have photon limited sensitivity, background limited sensitivity, and because even a perfect detector is going to be affected by the random arrival times of photons. And if you're going to measure something to a part per billion accuracy, you got to have a billion squared photons coming in, and that's a large number of photons, so you need to have a large collecting area. The other thing is these signals are buried beneath competing polarized signals emitted by our own galaxy. So I'm showing here the intensity of the microwave background signal, so B modes at the current upper limits, and here's at R of 10 to the minus 3, compared to the polarized signal from synchrotron emission from ultra-relativistic cosmic ray electrons spiraling in galactic magnetic fields, and the signal from dust, which is polarized dust grains emitting in the far infrared. And you can see that either one of these guys here is bigger than our current upper limits and orders of magnitude larger than a minimal inflationary model might predict. So if we want to see these primordial signals, we have to pull out these confusing foregrounds to a part per 100 to maybe a part per 1,000 accuracy. And then we have a further problem that if we're doing this with an instrument, we have to make sure that when we're looking for these tiny perturbations on top of bright glowing backgrounds, that we're not seeing some confusing effect of our instrument itself. So the first challenge that we have is sensitivity. So the microwave background has this featureless black body at 2.725 Kelvin. In intensity units, it's 10 to the minus 18 watts per square meter per hertz per steradian. The signals we're looking for here are about a part per billion of that, 3 nanokelvin signals for a minimal inflationary model. So we have to, if we're measuring polarization, you have to measure the intensity in one linear polarization and compare that to the signal in the orthogonal linear polarization, and do that differencing to a part per billion accuracy, and that's a challenge. The first thing you run into is the photon noise. So let's consider an ideal detector that has a single mode bolometer with 30% bandwidth sitting near the peak of the microwave background. The noise on that from this photon arrival statistics is about 25 microkelvin root seconds. So if you want to reach a few nanokelvin and you say, okay, how many seconds do I need to observe to beat this down by the square root of time? You need 100 million seconds, or you need 100 million detectors. And you need that for each beam spot on the sky. And we heard today, if we want to measure the ultimate for CMB, we need something like 1 million or more beam spots on the sky. So now we've got 10 to the 14 seconds, or 10 to the 14 bolometers, or some combination of a large number of detectors times long integration times. And that's for perfect detectors. That's even before we started realizing that nobody can build a perfect instrument. So we're talking right off the bat about very large number of detectors looking for very long integration times. Challenge number 2 is the foregrounds. Jacques will be telling us more about the foregrounds in our next talk. But again, we're looking for signals here that are buried under a bright glow from either polarized synchrotron emission or polarized dust emission. These foregrounds are brighter than the primordial signal everywhere on the sky. There's no magical dark patch on the sky where there's a hole through our galaxy that we can see out through that hole to the background radiation behind that. Even the best, cleanest spots of our galaxy are 10 times or more larger than our signal we're looking for. So we have to map these polarized foregrounds over the whole sky to very good sensitivity over a very large number of frequency bands so that we can tell the foregrounds from the primordial signal by the fact that they have different frequency spectra. If you have enough frequency bands here and a good enough understanding of the physics of these, you can then sort these guys out based on their frequency spectra and by their different spatial distribution. The problem is that there's a lot of foregrounds. So a rogues gallery of foregrounds, we know that there are things in our galaxy that are definitely polarized. I've mentioned the synchrotron and thermal dust. Of course, outside our galaxy, there are radio galaxies. These are partially polarized and will give you fluctuations in the polarization direction on small angular scales. And then there's the lensing of the bright B modes, or bright E modes in the microwave background by the matter distribution in the universe. There are other foregrounds in our galaxy that are probably not polarized or not very polarized. There's free emission from electron-ion interactions in the interstellar medium. There's what's called anomalous microwave emission, which is thought to be electric dipole emission from very small dust grains or really soot in the interstellar medium. There's a line emission, the CO lines, C+ lines from molecular and hyperfine transitions in the interstellar medium. And there's the cosmic infrared background, which is the infrared radiation from external galaxies. Sorting all this out to a part per thousand accuracy and better is going to involve careful measurements at a large number of frequencies over a range of angular scales and a range of over most of the sky. And you have to be really careful when you're analyzing data here, because it's very easy when you're dealing with foregrounds that are at this level to fool yourself into thinking that you're seeing a primordial signal when you're not. And the problem is that these foregrounds are probably more complicated than your foreground model will allow you to fit. So let's take an example of just the dust. That's something I've been working on recently. Dust in the interstellar medium absorbs optical and UV photons and then re-emits that radiation in the far infrared. We see that polarized far infrared emission, and we must subtract it to part per thousand to part per 10,000 accuracy. So here again, we got the synchrotron and the dust, and I've taken an imaginary experiment with perfect, no noise at all in this case, and I've measured it in 8 frequency bands from 30 gigahertz out to 800 gigahertz, spanning the range here where the microwave background signal is large. And I want to test my ability to pull this out. So I generate a model, a synthetic toy model of the dust emission that's more complicated than our standard foreground models admit. Normally we fit this dust here as some sort of a modified blackbody. It's emitting with a blackbody curve at some temperature, with some amplitude, and then with a frequency-dependent spectral index. So it gets flatter and flatter as you go to longer and longer wavelengths. This is a very popular phenomenological model. It fits available data very well, but will it work to arbitrary accuracy? The problem is that the dust is unlikely to come to a single temperature everywhere in the universe, because again, it's a power balance between the incoming and the outgoing radiation. It's very unlikely that every dust grain in the universe comes to exactly one temperature. So let's take a toy model where the dust comes to a broad range of temperatures. Dust will absorb a photon and start to emit. It emits that over a series of far infrared photons, and it spends a long time sitting here cold and a little bit of time hot. So most of the dust in the universe is sitting here around 10 or 12 Kelvin. A little bit of it is kicked up into the 20 kelvins. And about 4% of the power is sitting down here because cold things don't have a very large amount of power emitted. If I take this as my true model of sky, I generate that synthetic sky, but I fit it with a very simple model here, I find a very disturbing answer. I get a residual signal for my microwave polarization that's about at the R of a few times 10 to the minus 3 here, and that's when my input model had no polarization in the microwave background, so I'm getting a false detection of a B-mode signal here. The problem is that my chi-squared, my ability to fit this guy here is quite good. This model here, fitting this very simple model to my complicated input, matches the brightness distribution in the sky to 30 part per million precision or better in each one of my frequency channels. So if I'm relying on a chi-squared kind of test to tell me that my model here is giving me the wrong answer, I need to have part per million, 30 part per million precision in each of my frequency channels, and that's much higher than anything we've been talking about so far. So this is a very scary example where you can, using too simple a model here, gives you the wrong answer but doesn't tell you you've got the wrong answer. You look at your chi-squared and you say, great, I've got a chi-squared per degree of freedom of 1. Everything's wonderful. I've just won the Nobel Prize. But in fact, the universe has fooled you. The problem with parametric models, you have a lot of free parameters. With 7 free parameters, you can fit a charging rhino. We're unlikely to get this solve this problem by just coming up with better models. You need to get better data. So in order to sort out the dust here, you need to measure frequencies above a terahertz, where you can start to probe the wean tail of the distribution of the dust. Or you need to get the high sensitivity of something like a few times 10 to the minus 6 in delta t over t in each of your frequency channels, so that when you get a fit like this that's giving you the wrong answer, now your chi-squared waves a big flag and says, hey dummy, you screwed up, go back and try a different model. And either one of these is experimentally a design challenge that we'll be talking about through the rest of this workshop. The last thing, of course, here is systematic errors. You don't want to have your instrument screw you up. What you don't know about your systematic errors can, in fact, come up and bite you. So the fact that you haven't seen a systematic error so far in our successful instruments doesn't mean that systematic errors won't come up and bite you when you try to do a factor of 10, 100, or 1,000 times more sensitive. So the problem, again, with systematics is we're trying to measure a nanokelvin signal, and everything in the universe is hotter than a few nanokelvins. In particular, your instrument is going to be hotter than a few nanokelvins. Stray light of bouncing around within your instrument is hotter than that. And if you're trying to measure a bright 3 Kelvin signal in polarization and figure out what part of polarization is sitting there at this part per billion level, it means your calibration has to be accurate to a few parts per billion, and that's a very challenging thing, because typically we understand our calibration at the few parts per thousand, not the few parts per billion. Well, the secret to this, the solution to this is well known to the experimental community. It's to do a differential measurement. So you're not trying to just take something here and split the polarization into an X and a Y component and measure them independently and compare these after the fact to part per billion precision. What you want to do here is have something that rapidly chops back and forth between your orthogonal polarizations, and then you look for the demodulated signal here that matches your chopping. So you don't care about the unpolarized 0 level. You just let that go, and you look for the small modulated signal here that depends on your polarization state. And that means that you're now no longer sensitive to this bright unpolarized signal. If you measure 0 here, it means that your sky is unpolarized. If you measure a modulated amplitude as you chop back and forth, now you've got a polarized signal, and a gain error in that is much less scary. Because now it's just, okay, if I thought it was 3 nanokelvin and I'm off by a part per thousand, it's 3.003 nanokelvin. I could probably live with that. So you don't get the wrong answer. You just get, you can only ascertain the energy scale of inflation in this case, to a part in 1,000, which I think we would accept as a useful result. Of course, other things can go wrong with your systematic errors. You can have, here's a little toy here showing a telescope with beams to the sky bouncing off to your detector, and you have to worry about control of stray light within your instrument. So the red line here is showing, something from your detector looking out that bounces off a corner of your reflector here and goes somewhere else within your instrument. And you have to wonder about where are these stray light signals going and what are they seeing. So this is going to go to some part of your instrument that's at some temperature, and it means that your emission from the instrument here is at some temperature, and that was supposed to go to the sky. So you're comparing the difference between your instrument and your sky signal there. Your error signal then goes like the temperature difference between your instrument and the sky. That means if you want to get rid of this class of systematic errors, the way to do that is to make your instrument be the same temperature as the sky, or at least as close as you can. If you have a room temperature instrument that's at 300 Kelvin, the sky is at 3 Kelvin, that means your error signal here is modulating off of a 300 Kelvin big lever arm, and you have to control your instrumentation to extreme accuracy. If you can get this down to cryogenic temperatures, 4 Kelvin for liquid helium, now this is only a Kelvin or so, and you've made your error signal go down by 2 orders of magnitude just by cooling your instrument. If you can control your instrument very close to the 2.725 Kelvin temperature of the microwave background, so that this error now is only a few millikelvin, you've made that now another factor of 1,000 better, so you're 100,000 times better than an instrument at room temperature. So this kind of thinking here drives you to having cryogenic instruments and to keeping them as close as possible to the microwave sky temperature as you can. Where would you want to put your instrument? The easiest thing, of course, is to put it on the ground, but there's a problem with ground-based cosmology, and it's cold weather. We live within an atmosphere. It's nice to have that atmosphere to be able to breathe, but the atmosphere is not perfectly transparent, and that transparency varies as a function of time, and it varies as a function of frequency. So I'm showing here the atmospheric transmission. There are these windows where you can have reasonably see through the atmosphere, but only up to about 200 gigahertz or so. At higher frequencies, which you need to understand the dust foreground, the atmosphere becomes quite opaque. Then the atmosphere itself is turbulent, so the ability to understand fluctuations in your signal on short time scales, sort them out from your scanning strategy further complicates that. So you'd like to get away from the atmosphere if at all possible. Balloons can help. You can put your instrument on a stratospheric balloon, take it up to about 35 kilometers. You're above 99.5% of the atmosphere. So atmospheric emission and turbulence are no longer important. You have access across the electromagnetic spectrum, but you have short integration times. You can only really hang on there for so long. Conventional flights from mid-latitudes will get you, overnight flights, 10, 20 hours of integration. You can go down to Antarctica and fly around the continent, get 10, 20, maybe 30 days of integration. NASA is now developing ultra-long duration balloons that would launch out of New Zealand and go around the Southern Ocean for maybe up to 100 days at a time. But still, the maximum you're talking about is 100 days of integration. And remember that number I threw out earlier, where you need 10 to the 8 seconds in each of 10 to the 8 kilometers. 100 days is about is going to be about that 10 to the 8. If you get 100, if you only get at the 100, that's right, 10 to 8 seconds is 10 times worse than that. So you would need 10 of these flights here in order to get the sensitivities you need. So the obvious answer is to go to space. In space, you can just let it all hang out here. You get long integration times. We've seen missions that have 10-year integration times. Access across the electromagnetic spectrum from megahertz up to terahertz frequencies. Very stable thermal environment if you go to somewhere nice like L2, so you no longer have lunar emission or eclipses. There's no atmospheric noise, turbulence. There's no far field reflections from trees and mountains off there in the distance, bouncing signals back to you. It's the perfect place to be. The problem is it's expensive to get there. The ride out to there, the rocket ride starts at $70 million and goes up from there. So you're talking large bundles of cash if you want to go out to space. Now, when we're talking specific instrumentation choices, there are two ways that the experimental community has developed so far in order to get this combination of frequency coverage, sensitivity, and immunity to systematic errors. And I'm going to spend a few minutes here to just talk about this split, because if the goal of this workshop is to come up with a next generation architecture, it's useful to understand what's driving the two different concepts for instrumentation. So you need to get, again, the name of the game here is to collect a lot of photons at a lot of different frequencies. One way of doing that is you have single-moded optics. You're looking at the sky through some optics here, and you focus it down onto a focal plane. You get diffraction-limited resolution in each of a bunch of different pixels, but you need a lot of pixels in order to get a lot of photons. So this is a very simple architecture. We're talking, for next-generation instrumentation, we're talking about maybe getting a single mode in each of 10,000 detectors. An alternative is to use multimodal optics, so you're doing interferometers here. You take that same sky, the same optics, but instead of focusing it down on a bunch of pixels, you dump it into a concentrator with some sort of a phase delay above it. So you've got the same number of photons going in here now, but now it's got coarser angular resolution, and your phase delay up here allows you to pull out frequency information without a whole lot of different bandpass filters. You have to conserve the étendue, which is a product, the collecting area times your solid angle to the sky. But in a mode like this, the number of modes goes like A omega over lambda squared. And if you work out the numbers, say at 150 gigahertz here, you can get something like 10,000 modes on each single detector. So broadly speaking, one mode on 10,000 detectors or 10,000 modes on one detector, roughly comparable sensitivities, but different pros and cons for the individual architectures. How does this, how do these interferometers work? I think we all have a pretty good understanding of intuitively of how do you just focus light down onto a single bandpass limited detector. Fourier transform spectroscopy is not quite so well understood everywhere, but the basic idea is you focus light down here, you introduce a phase shift, optically usually by moving some mirrors around. All the power hits the detector all the time. As you vary your mirror position, you generate a fringe pattern here, and you just sample that fringe pattern as a function of mirror position, and then take the Fourier transform. The Fourier transform of the fringe pattern is the frequency spectrum on the sky. So basically you're taking this fringe pattern and just fitting cosines to it, and cosine of 2 times the period, cosine of 3 times the period, and so forth. Those Fourier amplitudes turn out to be the frequency spectrum of the sky emission. So very, very simple concept, and it has some nice features. If you look to say how to get my channels out of here, the maximum phase delay in your optical system sets the frequency resolution of the instrument, and as you sample this, you just get your frequency channels at 1 times that frequency, 2 times that frequency, 3 times, and so on. So if your frequency here was, say, 30 gigahertz, your channels would start at 30, 60, 90, 120, and so forth. And it goes up to some frequency, n over 2 times your frequency resolution, where n is the number of samples that you took over your fringe pattern. So very simple way to get access to high frequencies. Which is better? It depends on what you're most worried about in your instrument and your experimental design. So one of the trades you're making is angular resolution. For a photometer, you get diffraction limited resolution. Your A omega is just given by lambda squared. And if you have, say, a 2-meter mirror at 150 gigahertz, you're talking about arc minute resolution. So if angular resolution is your thing, this is a good choice. Your Fourier transform spectrometer here, you're taking, again, your A omega now is constant. So if I take a 2-meter dish and I work out, again, at 150 gigahertz, you get something like 30 arc minute angular resolution now that is independent of frequency. So that 30 arc minutes goes from your 30 gigahertz channel up into your terahertz channel. All your channels have essentially the same beam pattern. So if you care about angular resolution, you would go with a photometer, because it's in order to make this guy here arc minute, you have to make the thing 100 times bigger. And it's going to be very hard to put a 200-meter dish into space. Sensitivity. Sensitivity is dominated by the photon noise, which is proportional to the power on your detector. If you have a photometer, you can, with a whole bunch of frequency bands, you can chop that up. And the parts of the sky here where it's dark have lower noise. The parts here where frequencies where it's brighter have higher noise. And your sensitivity depends on your frequency resolution. A Fourier transform spectrometer, all the power hits the detector all the time. And so it's intrinsically a noisier measurement. And it works out to be about a factor of 2 or so noisier after you average all your channels together. So again, if sensitivity per unit time is your defining goal, which it could be for, say, a balloon-borne experiment, for instance, where you have a finite integration time, then again, a photometer is the way to go. If you want a bunch of spectral channels to sort out the foregrounds, now maybe the advantage switches the other way. A photometer, each channel, if you have a bandpass limited detector, every time you want a different frequency channel, you got to put a different detector in there. So the number of frequency channels depends in part on the number of detectors you have. For a spectrometer, you get many channels per detector because the frequency resolution just depends on the sampling of your fringe pattern. If you want a bunch of frequency channels, you just sample faster. So you get many channels per detector, and the advantage there would go to a spectrometer. Channel shape can be important. Here's the bandpass of the Planck high-frequency instrument. For a photometer, these bandpasses are set by filters, so it's microwave filters, quasi-optical filters. These can have a complicated shape and are hard to control at the percent level, so you have to go measure them in the lab before you fly, and that's a time-consuming thing. For a Fourier transform spectrometer, the channel shape is completely determined mathematically by your apodization, your window function, the weight you give to each of your measurements as you sample the fringe pattern. So this is something you can completely under your control here. And you can get very clean beam patterns with only a few percent channel-to-channel leakage. So if we want to say, look ahead to the future here and say, where do we go from here with these type of things? What can we expect from a future CMB space mission? So I will look into my crystal ball here and see where we might be going in the future. We can certainly take some guidance from the past. We've had 3 missions now dedicated to cosmic microwave background. There's the CMB Mission, which confirmed the black body spectrum and discovered the density perturbations. WMAP came about a decade or so later, measured the temperature power spectrum, saw the first evidence of superhorizon modes, and got a first look at the polarization. Now, most recently, ESA's Planck satellite has measured the temperature power spectrum to very high precision, measured the polarization spectrum, at least the E modes, to comparable high precision, and has now started to measure the lensing power spectrum. So we're a dramatic confirmation of our lambda CDM paradigm. So space missions are clearly the way to go for precision cosmology. But recently, attempts to get a 4th mission out of funding agencies have run into some problems. I note that baseball season, Major League Baseball, starts up next week, so we can take some baseball analogies here. A swing and a miss here. ESA's core, the core proposal was an imager that was proposed but not funded. NASA had the PIXI spectrometer, proposed and not funded. PRISM combined an imager and a spectrometer, proposed but not funded. And now LightBird is under consideration. It's reached a phase A study from JAXA, but it has not yet been approved for flight. So, we look at our crystal ball for space missions, we get, funding hazy, try again later. Meanwhile, we're getting steady progress from the balloon and ground-based instruments because they operate under a different paradigm here. In baseball, talk here, they can do small ball incremental approach. You can slowly upgrade your instruments over the course of time. Whereas if you're going for a space mission, you have to show, if you're asking for a couple $100 million, you have to show order of magnitude or better improvements over the current state of the art. So the ground-based missions are useful for a slow, steady, incremental approach, and then we have to try to combine the knowledge from those to put a mission together where we can really swing for the fences and try to get a ultimate CMB mission that will knock the ball out of the park here and hopefully either detect the inflationary signal or have an upper level, a non-detection at a level where it tells us something to guide future theoretical developments. So just to conclude, we're at a point now where the technology enables us to at least contemplate a future mission of this sort, where we can get to R of 10 to the minus 3 or 10 to the minus 4. That would allow us to make a very powerful test of the inflationary paradigm. If we were to see it, it would be a wonderful discovery. If we were to get an upper limit at those levels, it pushes us in different directions, and that's also a useful thing. Technology now allows this to happen, so let's stay tuned and see if we can come up with a measurement here that will allow us to actually do this. Thank you.